Okay, so I'm going to tell you about Lagrange's theorem, which is a theorem in group theory. I hope you know some group theory. Maybe you haven't seen a video about it recently. And Lagrange's theorem, it says this: let H be a subgroup of G. So that just means it's like a subset and it's closed. Then the order of H, or okay, let me say it like this: if you look at the set of cosets of G by H, which is like the set of all GH, so these are called cosets. Then and we actually call this something. You can prove this as a group. We call it G mod H. This is basically what G mod H is. And the cool thing is that G mod H, the order of G mod H times the order of H is equal to the order of G. Okay, so now I'm going to prove this. And the proof is basically, we basically just need this one lemma, which is that the cosets partition the set. So, and more formally, and I'm going to be kind of loose about whether or not the group is abelian or not, but okay. So more formally, xy is equal to yh if and only if x is an element of yh. Okay, so let's just prove this. If x is an element of yh, then this implies that x equals yh for some h, such as this, okay. And then we can use inverses to get, so now we're going to show that any element of xh. So let's look at another element of xh. So then xh1, I'll call this xh0. So then xh1 is equal to yh not h1, which obviously is y times h2 for some h2, which belongs to yh, so that's pretty good. And then on the other side, if we have yh1 or something, like yh3 for instance, then this is equal to y times h0 times h0 inverse times h3, right, I just kind of rewrote it, but this is equal to x times h0 inverse h3, and that obviously belongs to xh. Cool, so that's one direction. But now what about the other direction? So for the other direction of this proof, let's say that xh equals yh. So okay, let's assume for contradiction that x is not an element of yh. So x is not equal to y times h for any h. But this is actually a real big problem because x belongs to xh. So then, but this is saying that x does not belong to yh. So that obviously can't be. So this implies x is in xh, but it's not yh, so that means xh not yh, which is a contradiction. Alright, so we proved the lemma. Cool, so now using the lemma, because of the lemma actually implies that, given x, y in the group, either xh equals yh, or xh intersect yh is equal to the empty set. And this is a pretty straightforward consequence of the lemma. Okay, I'll formally prove it though. So imagine xh equals, imagine x, okay, it's actually just a straightforward, like exactly a consequence of the lemma. Because if xh belongs to yh, so if xh intersect yh is not the empty set, then there exists a z belongs to xh intersect yh, and then that means that we can write z as xh1 and yh2, which is exactly the condition x belongs to, like, okay, so x equals yh2 h1 inverse, so x belongs to yh, exactly the condition we had. Okay, so this means that they're all the cosets are going to be, actually cosets, like taking cosets partitions the set. So what does this mean? It means, and okay, there's one more thing that you should know, is that if we look at any coset, the number of elements in it is actually just the number of elements in H, because you might be concerned what if xh1 equals xh2? Well, actually it turns out that this is going to imply x equals xh2 x1 inverse, which implies that h1 equals h2, so there's no problems. So this is true. Okay, so then to finish up the proof of Lagrange's theorem, you can look at all those cosets, and in any one of those cosets, the number of elements is H, so, and the cosets are going to partition the set, so that means that G over H is the number of cosets, and by definition, that's the order of the set G mod H, the quotient group. So that's Lagrange's theorem.